Good morning, everyone. We're going to be looking today at the magnetic force that is acting on wires carrying electric currents when you put those wires in a magnetic field. We've already looked at magnetic forces that act on a single moving charge, and I want to talk briefly about those forces. When you have a charge in motion, there's a little tiny magnetic field that encircles it. If that charge carrying that little tiny circular magnetic field enters another magnetic field, we call that other magnetic field an external magnetic field. But if that moving charge that's carrying its own little magnetic field with it everywhere it goes enters another magnetic field, then those two magnetic fields interact. And the result of that interaction is a magnetic force. And it's a magnetic force on the charged particle. We're going to make the same kind of argument as to why there ought to be a magnetic force on a wire carrying a current. Near the beginning of this unit, we learned something about electricity and magnetism, and that's that if you have a flow of electrons in a wire, if you have a wire that carries an electric current, then you will get a magnetic field that encircles that wire. And this is just a diagram of a demonstration that we did. We had a vertical piece of wire that was connected to a high current power supply. And when we placed a number of different compasses in different locations around the wire, the compasses all pointed in these directions that formed a circular pattern. And the result is that we get a circular magnetic field. I don't really care too much here about the details of this diagram. You should know that conventional current is the direction that positive charge would flow if positive charge did flow in a circuit. It doesn't. Electrons really flow. You should know, looking at this diagram, that this is the negative terminal of the potential difference and this is the positive terminal of the potential difference. And you should know how to use what I call the curly right-hand rule. But the more general point, which is the most important point, is if you have a wire carrying a current, there will be a magnetic field attached to that wire. So as a result of that, if you were to take that wire, which now has a magnetic field around it, and you put that wire in another magnetic field, well, the magnetic field that you put the wire in and the magnetic field that the wire has surrounding it are going to influence each other, and that influence is going to be a magnetic force. Now, just like we have a formula for the magnetic force on a moving charge, the magnetic force on a moving charge can be calculated by taking Q times V times B. We have a formula for the magnetic force on a wire carrying a current. And basically, if I strip this formula of all of its decoration, the magnetic force on a current carrying wire is the current in the wire, which is I, times the length of the wire that's in the field, which is L, multiplied by the magnetic field strength, which is B. I don't really care about the perpendicular symbol there. I just want you to focus on the fact that L is the length of the wire that's in the field. And then if we want to find the direction of the magnetic force, we're going to use the second right-hand rule. This is the same second right-hand rule that we've used before. This is not the curly right-hand rule. This is the one where you put your right hand flat and the magnetic field is the direction of your fingers. And I really hope that you're looking at your right hand right now as I'm going through this. The magnetic field is the direction of your fingers. Your thumb points in the direction of the motion of the charge. And if the charge is positive, the force is out of the palm of your hand. And if the charge is negative, the force is out of the back of your hand. So in this formula, as I said, I is the current in the wire. It happens to be measured in units called amps. And the length of the conductor, L, must be the length. Again, I don't care about the perpendicular part. What I really want you to focus on is it's the length of the conductor that is in the magnetic field. So for example, if your magnetic field occupies a region of space represented by this, I don't know how we've created this magnetic field. I don't know the direction of the magnetic field. and I don't care about any of that. All I know is that there's a magnetic field in that region. So there's some magnetic field here. And I have a wire. Let's take a piece of wire, big thick copper wire, and I connect that wire to a potential difference. Then there will be a current in that wire, and since that current carrying wire is in a magnetic field, it will be forced. The point I want to make, it's what's highlighted in yellow. The point that I would like to make is that L is this distance. It's only the length of the wire that's actually in the magnetic field. And then B, of course, is the magnetic field. We're going to do a demonstration now, and the demonstration will hopefully get across how the right-hand rule works for current-carrying conductors. What I have here, let me just explain what this is in general, and then we'll get to the specifics of it. We've got a power supply, which is going to produce a high current, and connected to that power supply is a circuit. So you can see the wires coming out of the power supply. This is the power supply. The wires are coming out of it, and there's a positive terminal and there's a negative terminal, and that forms a complete circuit. I'm going to go to a different diagram here to show you where the circuit is. And I think what I'll do is I'll trace out the flow of electrons. Electrons are negative, and they will be repelled from the negative terminal of the battery. So they are going to follow this path, and they will get to here. And it's hard for me to show you without hand motions, but what we've got there is a U-shaped piece of metal. I'm going to add something to this diagram, and then I will immediately get rid of it. We've got a U-shaped piece of metal which comes all the way down, goes in, and then goes up. And it's behind here. And that U-shaped piece of metal is pivoting on a balance point. The balance point is right in here. So this whole thing can swing. There's something else down at the bottom that's kind of obstructing your view, but we'll get to that in a second. In other words, if you were a little tiny person and you were sitting on this swing at the bottom, then you would be able to swing back and forth. Okay. So I'm going to get rid of that now and get back to the path that the electrons follow. So the electrons get to this part of the U-shaped conductor, or swing. Now what they're going to do is they're going to go down because they are attracted to the positive, and we're following this around until we get to the positive. They will go up here, and there is a connection here that leads to this lead, which goes back to the positive. So the end result is that when we plug this in, you have electrons flowing in that U-shaped swing, which is a conductor. If we take a closer look at the U-shaped swing, and the way I just drew it, the electrons were traveling this way, we can see that there's a set of magnets at the bottom. And the way this is currently set up, what I have are magnetic field lines which would be going from the north pole of this magnet to the south pole of the other. So we have magnetic field lines going from the bottom of the page to the top of the page, and we have electrons that are flowing into the page. So what should happen, here's our magnetic field labeled, here's the electron flow labeled. What should happen is each electron in that conductor should be forced due to the magnetic influence of its magnetic field and the magnetic field it's in, and as a result, that whole bar on the bottom, that whole bottom should be forced. So what we're going to do now is look at a video of the demonstration, and I'm going to splice it in with this, and then once we're done with that video, we'll continue with the lesson. Okay, so what we're looking at here is a zoomed in view of the apparatus that we were just discussing in the video a few seconds ago. You can see the high current power supply that's on the right, and it's currently off. And you can also see the bottom of the U-shaped conductor. Remember that U-shaped conductor is free to pivot at the top. It's acting like a swing. So the bottom of that conductor is free to move back and forth. And currently right now it's just hanging freely under the influence of gravity. You can also see that I put that pink piece of paper there, and I'm reminding you that that little pink piece of paper taped to that bottom of the conductor is what we want to focus on. When I talk about the conductor being in the magnetic field, it's that part of the conductor that's in the magnetic field. And I have it set up right now so that electrons in that part of the conductor are flowing from the front to the back. So from your perspective, watching this on a screen, the electrons are flowing away from you or into the screen. And that's why I have an arrow in the indicated direction on that sheet of paper on the tabletop. The magnetic field I have set up so that the magnetic field going through that part of the conductor that's labeled with the pink paper, the magnetic field is from the bottom of the screen to the top of the screen. So that's indicated by a series of those circles with dots in them that mean out of the plane of paper. So the magnetic field, again, that the pink labeled part of the conductor is in, the magnetic field is towards the top of your screen. In a second, I'm going to ask everybody to pause the video so you can use the right-hand rule to predict the direction of the magnetic force on the conductor when I turn the power supply on. You're going to use the right-hand rule to do that, so go ahead and pause the video, and when you're done, unpause it to resume. Hopefully everybody predicted that the magnetic force acting on the conductor is going to be to the left. If you use the right-hand rule, and I can't fit my hand in that little tiny space where the pink label is on the conductor, so you're just going to have to imagine that it's in there. When I point the fingers of my right hand towards the ceiling, which is the direction of the magnetic field, and my thumb out, which is the direction of conventional current, then the palm of my hand faces the left, and that means the force is to the left. If I wanted to focus my attention on electrons, then I would have to have the fingers of my right hand towards the ceiling, but then I would have to turn my hand around so that my thumb is in the direction of electron flow, which is into your viewing screen. And since I'm focusing on electrons, the force is out of the back of my hand, which is still to the left. So no matter how you cut it, when you use the right-hand rule to predict the direction of the force, it will be to the left. So I'll turn the power on now. And you can see that it is forced to the left. Not a lot, but it is definitely forced to the left. It is further to the left now than it was before. If I were to turn the current up, we would predict that the force should be greater. The reason the force is going to be greater is when the current increases, the electrons moving in the conductor move more rapidly, and each of those little tiny electrons, when it's moving, has a magnetic field around it. It's that magnetic field which pairs with the magnetic field of the magnets that produces the force. So if I increase the speed of the electrons, that little tiny magnetic field around each electron is increased, so the force will increase. And I've cranked it up now to about 4.7 amps, and you can see it's considerably further to the left. It's wobbling around just the way any other swing would wobble around until it finds an equilibrium. If I were to increase the current even more, it's forced more, but it doesn't appear to move as much. And the reason is, that's the end of the magnetic field. The magnetic field doesn't exist further to the left of where that pink piece of paper is. But I could very easily take the magnetic field and extend it further in that direction, and as a result, you can see that it is deflected even more. One other thing that we learned, I'm just going to turn this down a little bit. One other thing that we learned is the amount of the magnetic force is also determined by the strength of the magnetic field that the conductor is in. So I'm at about 1.6 amps right now, and I'm looking square on the front of this apparatus, and I'm looking at an angle of about 5 degrees. It's just a little bit less than 5 degrees, but basically that swing is deflected 5 degrees to the left at 1.5 amps. And I can see the power supply is wobbling back and forth sometimes from 1.5 to 1.6 amps. If I want to increase the strength of the magnetic field, then I suppose I could use stronger magnets, or what I could do is take these magnets off and move them closer together. And when I move them closer together, I'm going to get a stronger magnetic field. So I'm going to put this back in the same location that it was at before and wait for it to settle down. And I can already see that it's further than 5 degrees off. Not a lot. I would probably say it's 6 to 6.5 degrees, and it was at 5. So the strength of the magnetic field also affects the amount of the force. The third thing that we talked about, I can't really demonstrate with this. The third thing that we talked about is the amount of the conductor in the magnetic field. And in order for me to get more conductor in the magnetic field, I would have to have magnets that had a greater surface area, or I would have to wrap that conductor around in loops over and over again so the conductor keeps getting duplicated in that magnetic field. Of course, the problem with that is if I have more loops of the conductor, it's going to be heavier, and we wouldn't necessarily see a change in the magnetic force. Just one last quick thing here. It doesn't really matter what the orientation is. Just going to adjust this so it's hanging freely again. There was a bit of friction at the top. If I were to take and reverse the polarity, but keep the magnetic field the same. So what I'm going to do is I'm going to switch the leads on the power supply, so now the electrons in the bottom of this are going to be coming out of the screen towards you, but I'm going to leave the magnets alone. And again, there's a little bit of friction acting here, so I'm just adjusting. There's something I can adjust on the top to kind of straighten it out. It's pretty much hanging freely. So now what I'm going to do is I'm going to switch the leads. And by switching the leads, that means the electrons will end up traveling in the opposite direction. And we could use the right-hand rule to predict what would happen here. If the magnetic field is towards the ceiling, my fingers go towards the ceiling, my thumb can be electrons this time, and the back of my hand is facing to the right, so the force is to the right. If I turned my hand around this way so that I could say magnetic field is towards the ceiling, and conventional current is in, which it is, then the force would be out of the palm of my hand, which is still to the right. So when I turn this on, you can see that it's forced to the right. And again, I can increase the current to get a greater force. Of course, it's bumping into the edge of the magnets there, so I could move the magnets to give it a little bit more breathing room and force it even more. So that's just a demonstration of the magnetic force acting on a conductor that's carrying a current. This, of course, is called the motor effect. So hopefully that gave you some practice with the right-hand rule. Let's take a look at the examples now. It's only one example we're dealing with today. We've got a situation where we have two magnets creating a magnetic field, and you have this cylindrical conducting wire that has a certain mass, and it's in between the poles of those two magnets. The magnitude of the magnetic field in between those two poles is 95 millitesla, and the current, when you first turn this on, is 3.1 amps. Okay, let's take a look at the first question. The first question is, what's the magnetic force acting on the wire? Well, this is really a simple question. It's Fm equals ILB. So we're going to take the current, which I believe was 3.1 amps. We're going to multiply by the length of the conductor in the magnetic field. It says it's an 82 centimeter length that's lying perpendicular to the magnetic field. So the implication is that the distance that's actually in the magnetic field is 82 centimeters. It doesn't matter how much it extends beyond it. We're told 82 centimeters is perpendicular to that magnetic field. So L is 0.82 meters, and then we have to multiply by the magnetic field, and the magnetic field is 95 millitesla. So just grab a calculator and see what we get. I wrote 95 millitesla. That means I have to actually go 95 times 10 to the negative 3. So I have 3.1 amps, I have 0.82 meters, and then I have 95 multiplied by 10 to the negative 3, which gives us a force of, a magnetic force that has a magnitude of 0.24, that I see 12149 newtons. Now we're not done here because you're asked to determine the magnetic force, but magnetic force is a vector, so we need to determine the direction of that magnetic force. Well, we take a look at the diagram. This is awfully big, but I'm not going to try to draw my hand here. You have to use the flattened right-hand rule so that your fingers point in the direction of the magnetic field. Your thumb points, now you have an option here. I'm an electron kind of person. So the electron flow in this conductor is this way. So you need to use the right-hand rule now to predict the direction of the magnetic force on that wire. You can pause the video, figure out the direction, and then resume the video. I get a magnetic force that's towards the top of the page. I'm just going to use a different color here that shows up a little bit better. So if I point the fingers of my right hand left to right, which is the magnetic field direction, and my thumb in, the back of my hand is facing the ceiling, which is towards the top of the page for me because my smartboard is vertical. So I get a magnetic force that's towards the top. The magnetic force is up. So the magnetic field is to the right, the electron flow is in, the magnetic force is towards the top of the page. So we should put that in with our answer. The magnetic force is 0.24149 newtons toward the top of the page. And I'm not really concerned about the number of significant digits, so let's not worry about that. Hopefully that made sense. One more little question, which asks us to determine the net force acting on the wire. Well, normally we go through this discussion where we talked about this in the last video, where the magnetic force was the net force, and the reasoning behind that statement is that the magnetic force was the only force, and a lot of the time it's the only force. But in this question, they make a big deal of telling you the mass of the wire. The mass of the wire is 28 grams. This isn't an electron or a proton whose mass is so small we can ignore it. We have to consider the fact that although there is a magnetic force up, there is also a gravitational force down. Now, I don't know how large the gravitational force is, right? I don't know how big this force of gravity is. But if the force of gravity is bigger than the magnetic force, which is up, then to find the net force, I would take the force of gravity and subtract the magnetic force. If the force of gravity is smaller than the magnetic force, then I would subtract the other way. Who knows? Maybe the two forces are exactly equal, in which case that conductor is going to be suspended because the forces are balanced. So in order for us to answer this question in B, we actually have to find the gravitational force first. Well, let's just calculate the gravitational force. It's m times g, which is 28 grams, 0.241 0.028 kilograms times 9.81 newtons per kilogram, what we get for a gravitational force is 0.27468. Newtons. So what we're dealing with here, I'm not going to draw the three-dimensional diagram. I'm just going to draw the end of the wire. This is the end of the wire. We're dealing with a magnetic force equal to 0.24149 newtons. I'll double check that number in a second. We're dealing with, I just want to rewrite it, the magnetic force of 0.24149 newtons. And we have a gravitational force which is slightly bigger. The force of gravity is 0.27468 newtons. I just want to go back and check to see if that 0.24149 is right. Yes, it is. So what we have is a gravitational force which is greater than the magnetic force. I haven't drawn this to scale. I don't think it's that much greater, but we can go ahead and subtract those two magnitudes in order to determine the resulting sum, which is the net force. Maybe what I should do here just before I do that is make sure that you understand that the net force is the sum of the two forces. But when you add forces, you add them taking direction into account. And when you have two forces that are in opposite directions, when you add them, you find the magnitude by subtracting the values. So what we're really doing is taking, if you wanted to be very clinical about it, we're taking positive 0.24149 newtons, and we're adding the force that's downward, which is negative 0.27468 newtons. And then you're going to get a negative result, which means the net force is down. I don't know that you need to do it that way, but I just wanted to point it out because some people might choose to. Personally, I would just take the bigger force and subtract the smaller force to get 0.03319 newtons. And if you do it using this method on the board, you'll get negative 0.03319. If you did it just using my kind of intuitive approach, you took the larger force and subtracted the bigger force, which means you're getting the extra amount of force downward, which means the answer is 0.03319 newtons toward the bottom of the page. And that's it for that example. And in fact, that's it for the lesson. So you don't have a lot of work to do here to check your understanding. There's 5 problems that I've typed up for you on the next page. Remember that assignment number 1 is due tomorrow by 3:15 p.m. And also remember that tomorrow is a Google Hangout day. So if you have any questions regarding anything in period 1, check us out at the Google Hangout. We'll be there. Somebody will be there anyway. Hopefully I'm not alone, and I would be happy to help you out. So in the meantime, have a great rest of the day, and I will talk to you later.